The topic of the video is the time reversal operator for a system with no spin and a system with non-zero spin. The operation where t tends to minus t is called the time reversal operation, and then under this kind of transformation, the position coordinates r's will remain as they are, but the momentum operators, which we can write as p's, will actually have a change of sign. And if the commutators of x and px are considered before the time reversal operation and after time reversal operation, then we can actually prove that t, the time reversal operator t into ih cut into t inverse is equals to minus ih cut. So we can say from this fact that t should be antilinear operator. Next, we try to understand the equation for t for the case of a spinless system. If the Hamiltonian of the system is invariant under the time reversal operation, then the Schrodinger equation of the system with a state function psi rt can be written like this. And if we replace t by minus t in this equation, we get ih cut into dou by dou minus t and the rest of the thing. So here, when dou minus t is written as dou t, then the minus sign can go up. So therefore we can say that psi r minus t is actually not a solution of Schrodinger equation. But if you take the complex conjugate of the above equation on both sides, we get this equation, which says that psi star r minus t is actually a solution of Schrodinger equation. Therefore we can actually take that time reversal operator, when operates on state function psi rt, will transform it to psi star r minus t. So we take the time reversal operator t as a product of unitary operator u and then complex conjugate operator k sub c. And for a spinless system, we can even write this u operator as a identity operator I. So we can even write the time reversal operator t is equals to k sub c. And in case if the wave function was represented in momentum representation, then we can write t acting on psi pt is equals to psi star minus pt minus p and minus t. And next we discuss about the time reversal operator for the case when the particles have got some spin, particles or system has got some spin. Since angular momentum is actually a cross product of the position vector r and momentum vector p, then after transformation L prime is equals to minus L. Similar is the case even for spin angular momentum S as equation number 1. And for a system with a spin half, spin S is equals to 1 half, then we can write the components of spin angular momentum Sx, Sy, Sz in terms of the Polish matrices like this. And if you take T is equals to U into Kc, then equation number 1 for Sx, S component, x component of S will be actually written like this, where we have replaced this T dagger with K dagger and U dagger. Since the action of Kc on Sx will be just Sx into Kc, we get u Sx u dagger is equals to minus Sx. And similar is the case even for Sz. But for Sy, which has got complex quantities in its matrix form, when K sub c acts on Sy, it will actually give you minus Sy into K sub c. So we already have a minus sign on the right hand side, so the minus minus get cancelled, and then we get u Sy into u dagger is equals to minus Sy. I'm sorry, just Sy. So therefore we can actually say that u should represent a rotation of coordinate system through an angle pi about the y-axis in spin space, which we can actually written as exponential I by h cut into pi into sy. And in case if the system or particle has got total angular momentum j, then the operator u should be actually taken as exponential I by h cut into pi jy. So therefore the time reversal operator t can be written as a product of this exponential term and then the complex conjugate operator kc. If the state I mean if the basis state vector of the system in angular momentum representation is taken as ket j comma m, then if t acts on that, it should be giving you minus 1 power j plus m into j minus m. And if you operate t on it both sides, we get t square with eigenvalue minus 1 power 2j. And it says that t square has got eigenvalue of 1 for integer values of j and minus 1 for half integer values of j. That's it in this video. Thanks for watching.